Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum, Class 7, 4.3 Conservation of Linear Momentum, Collisions, Part 3. Then Section 1, Inelastic Collision, Adhesion. Adhesion means that the two bodies will stick to each other. Previously, in the previous video, we have seen that in collisions the linear momentum is conserved, and they can be classified into elastic and inelastic based whether the kinetic energy is conserved or no. One specific type of collision is when two bodies collide, stick together, and move as a one body after collision. This collision is classified as inelastic collision or completely inelastic collision, as the system loses kinetic energy. Objects or bodies during this collision might lose or gain kinetic energy, and this depends on the type of the collision, the type of interaction. However, always remember, in this type of collision, the system as a whole loses kinetic energy. The kinetic energy is mainly lost as heat or sound. So here we're saying that objects might lose or gain kinetic energy. But if we're talking about the system as a whole will lose kinetic energy, and the kinetic energy is lost as heat or sound. In the following section, we will demonstrate or anticipate different scenarios, starting with scenario 1. Consider a projectile of mass m is launched with an initial speed v0 and becomes embedded in a block of mass m initially at rest. Directly after collision, the system consisting of the projectile block will move together with the speed v. So here you can notice that initially we have a projectile with the mass m moving with an initial speed v0 to the left. It will stick to the block m, and after the collision they will move as one body with the mass m plus m and speed v to the right. Applying the conservation of linear momentum, P initial is equal to P final. Initially, only the bullet or the projectile has momentum given by P0 plus the momentum of the block, which is 0 because it's not moving, equals to P, which is the momentum of the system as a whole. Now that would be mv0. M plus m would be the total mass, and v would be the speed of the object. Now if we isolate v would be m divided by m plus m multiplied by v0. Then the final speed of the system projectile block, or the velocity of the center of mass directly after the collision, is given by v, which is a fractional mass, multiplied by v0. Now what would be the interpretation in this case? The final speed v of the system can be understood as the initial speed v0 factored by a fractional mass, which is very similar to at Hood machine. Now this is the fractional mass. The mass in the numerator represents the quantity of motion. If you look carefully to the numerator, if you expand this with this one, that would be mv0. What does mv0 represent? mv0 represents the quantity of motion before collision, because remember that the bullet was moving to the right with the speed mv0, with a momentum mv0. For this reason, in the numerator we would have mv0, which represents the quantity of motion. And the denominator, that would represent the total mass of the system or the inertial mass. Here the masses in the system that are involved is the mass of the projectile and the total mass on the mass of the block. For this reason we have the total mass of the system. The projectile loses kinetic energy. So here what we're trying to say is that when the projectile hits the block, it will lose its kinetic energy, and some of the kinetic energy will be transferred to the block. For this reason, the block gains kinetic energy. But the system as a whole, if we're talking about the system as a whole, it will lose its kinetic energy, which makes this type of collision an inelastic collision, or known as completely inelastic collision. Kinetic energy is not conserved. Now scenario 2, consider block 1 of mass m1 is launched with an initial speed v1 to the right, collides and sticks to a block 2 of mass m2 also moving to the right with the speed v2. Directly after collision, the system block 1, 2 move together with the speed v to the right. So initially what's happening is that we have two blocks given by masses m1 and m2. We have speeds v1 and v2, both of them are moving to the right, but the speed of v1 is sufficient enough in order to catch this block, and they will stick together. After collision, they will become one body of mass m1 plus m2, and they will move to the right with the speed v, as shown here in the animation. Now the aim in this section is to determine v in terms of the variables of the system, and this can be done by applying the conservation of linear momentum. Remember, if this is a free response, we need to mention apply conservation of linear momentum. Then P initial is equal to P final. Initially, what are the objects that are moving? Both objects are moving this with a momentum m1 v1 to the right, which is m1 v1, plus the momentum of the bigger block given by m2 v2. Then initially we have p1 plus p2, which is m1 v1 plus m2 v2, and after the collision they're moving as one body with a mass m1 plus m2 with a speed v, and we're interested in determining v. So v can be expressed as m1 v1 plus m2 v2 over m1 plus m2. Then the final speed of the system block 1, 2, or the velocity of the center of mass directly after the collision is given by the following. Now what would be the interpretation? The final speed v of the system can be understood as this initial speeds v1 and v2 factored by fractional mass. This is the fractional mass that we're talking about. Alright, here this is the fractional mass. The mass in the numerator represents the quantity of motion. So notice that here in the numerator we have this mass and this mass, m1 and m2, and they represent the quantity of motion because before collision both m1 and m2 they're moving. Now the mass in the denominator represents the total mass of the system or the inertial mass, independent whether m1 and m2 they are moving or no. Always in the denominator would expect that you would have m1 plus m2. Block 1 or block 2 might gain or lose kinetic energy, and this depends on the type of interaction. However, if we're talking about the system as a whole, for sure the system will lose its kinetic energy. Alright? Which makes this collision to be an elastic collision, or known as completely inelastic collision. So either we say inelastic collision or completely inelastic collision. Now scenario 3, consider block 1 of mass m1 is launched with this initial speed v1 to the right, collides and sticks to a block 2 of mass m2 moving to the left with a speed v2. Directly after collision, the system block 1, block 2 move together with a speed v to the right. So notice that here, in this case, both of them has momentum. This is to the right, m1 v1, and this is to the left, m2 v2. The difference between this scenario and the previous scenario is that now this is in reverse direction. And after collision, both they will move with an inertial mass m1 plus m2 with momentum with speed v. We assume that block 1 has enough momentum to change the direction of motion of block 2. Now let's apply the conservation of linear momentum. P initial is equal to P final. P1 plus P2 is equal to P, then M1 V1 minus M2 V2 is equal to M1 plus M2 multiplied by V. So here, why do we have the minus sign? Simply because before collision, the block 2 was moving to the left with momentum M2 V2. Then now, if we isolate V, then V is given by M1 V1 minus M2 V2 over the total mass. Then the final speed of the system, after they stick together, is given by M1 V1 minus M2 V2 over the total mass. What is the interpretation? The final speed of the system always and forever is expressed as a fractional mass multiplied by V1 and V2. The mass in the numerator represents the quantity of motion. The minus sign in front of M2 V2 indicates the opposition of motion. Now why this is plus? Because that would be the final direction of motion. Why this is minus? Because it's opposing the motion. The mass in the denominator represents the total mass of the system or the inertial mass. It's always given by the absolute sum. And block 1 or block 2 might gain or lose kinetic energy, and this depends on the type of interaction. So block 1 might gain or lose kinetic energy. In particular, it will lose, and this might gain or might lose. However, if we're talking about the system as a whole, it will lose its kinetic energy, which makes this type of collision an elastic collision, or known as completely inelastic collision. Now, the final scenario, which is scenario 4, consider block 1 of mass m moving to the right with a speed v0. Another block 2 of mass m is dropped and sticks to block 1, like the following. Now, the total mass of the system is given by capital and m. Now, here I didn't indicate the speed or the velocity of this block because we're considering the motion along the horizontal. Initially, it has vertical motion. After collision, both they will move to the right with a mass m plus m and a new velocity or speed v. Apply the conservation of linear momentum. P initial is equal to P final. Remember that this is a vector equation. It gives the birth of two linear equations. We're only interested along the horizontal. Initially, the block that is falling has a vertical velocity, but it has no horizontal velocity. For this reason, I will write P0 plus 0 is equal to P. P0 is the initial momentum of the block that is sliding toward the right with the momentum mv0. While this 0, although this block was falling down, but it has no velocity along the vertical, and that would be equal to m plus m, which is the total mass along with the new velocity, and we're isolating v. So the new speed of the system block 1, block 2 after collision is given by capital M divided by m plus m, and this is reasonable, as we shall see. The interpretation would be the final speed v of the system can be understood as the initial speed v0 factored by fractional mass. This is the fractional mass. Now, in the numerator, this represents the quantity of motion along the horizontal, and that would be represent the total mass or the inertial mass. Block 1 loses kinetic energy. Block 2 will gain kinetic energy along the horizontal motion only. So here, this was falling vertically. So it will lose kinetic energy along the vertical. However, it will gain kinetic energy along the horizontal. But the system as a whole will lose kinetic energy, which makes this type of collision inelastic collision, or known as completely inelastic collision. And now for the rest of the video, we're gonna solve some exercises. Exercise 1, a railroad car of mass 1500 kilograms rolled to the right at 4 meters per second and collides with another railroad car of mass 3000 kilograms that is rolling to the left at 3 meters per second. The cars stick together. Why sticking together is important? Because they will have a combined mass given by m1 plus m2. This is the mass m1, and that would be the mass m2. So let me write before collision what's gonna happen, and after the collision what will happen. Before the collision we have two objects, basically the cars. One of them is moving to the right with a speed of 4 meters per second, and the other one is moving with a speed of 3 meters per second. The first one has a mass given by 1500 kilograms, and the second one has a mass of 3000 kilograms. Now after collision, this is moving to the left because, this is important. After that, they will stick to each other, forming one mass of 4500 kilograms. Basically this plus that, and we want to determine the speed v at which it's moving. It might be to the left or it might be to the right. This depends on the momentum of each cart or of each car. Then if this is a free response problem, we need to say apply the conservation of linear momentum. Now even here, if they didn't mention that the system is isolated, we're assuming so, then P initial is equal to P final. Initially we have m1 v1 minus m2 v2 because this car is moving in the negative direction. Then we're gonna have a combined mass given by m1 plus m2 multiplied by v, and we're searching for v. V is given by m1 v1 minus m2 v2 divided by m1 plus m2. Now if you look carefully at the following fraction, it represents in the numerator the quantity of motion. This is helping, this is opposing because in the negative direction, and that would be the total inertial mass, and that would be given by m1, which is 1500 multiplied by 4 minus 3000 multiplied by 3 divided by the total mass, which is given by 1500 plus 3000, and if you plug that on the calculator, that would be minus 2 over 3 meters per second. The negative sign means that this has more momentum than the one on the left, and indeed 9000 is greater than 4 times 1500, so it will be moving with velocity 2 over 3 meters per second to the left, or speed 2 over 3, that would be A. A projectile of mass m1 is traveling with a horizontal speed vi to the right toward a block of mass m2 that is at rest on a horizontal surface as shown. The projectile becomes embedded in the block, and the block and the projectile move together to the right with the speed vf. So after collision, they will move together with the mass m1 plus m2 and with the final velocity vf. with the speed Vf. There is negligible friction between the block and the surface, which means that the system is isolated. Normal push, however, cancels with the pull of gravity. The duration of the collision between the projectile and the block is delta t. Which of the following expression is equal to the average force exerted on the block by the projectile during the collision? The average force is given by delta P divided by delta T, and that would be the average force exerted by 1 on 2 or by 2 on 1, and that would be equal according to Newton's second law. So this can be written as delta P1, which is equal also to delta P2 over delta T in magnitude, not as a vector quantity, because they're opposite in directions. However, if you're talking about delta P over delta T of the system, that would be necessary 0 because the system is isolated. Here we're talking about delta P1 and delta T2 solely, up to a negative sign that we don't care much about because we're interested in the magnitude. Now, what does delta P1 over delta T represent? It is the variation of the momentum of the projectile, which represents the force exerted by 2 on 1. Delta P2 over delta P2 would be represent the variation of momentum of M2, which represents the force exerted by 1 on 2. Now the thing is that in the numerator we only have one mass, which means that we need to consider the block M2 because it is initially at rest. However, we can calculate both of them and check which one would work. Let me do with delta P1 over delta T. So that would be M1 delta V1 over delta T. Why does delta P equals to M delta V? Because we know that P is MV and delta can be considered as a derivative. So delta, and here delta of MVM is a constant, can be dragged out. So delta P equals to M delta V. Now that would be M1 delta V1 over delta T. So here we have delta T, here we have M. What is the final velocity of the projectile? Since they're moving as a one body, then the final velocity is Vf, and the initial velocity is Vi, and the mass is given by M1. Notice that none of these has the same form, so let's try to work out delta P2 over delta T. So that would be M2 delta V2, which is V final minus V initial, which is 0 divided by delta T, and that would be M2 Vf divided by delta T, which makes E to be the correct answer. A large truck of mass 4m is traveling at a speed v when it collides with a small car of mass m that is at rest. So here we have 4m moving with a speed v. It will collide with the mass m that is at rest. After collision, they stick to each other and they're moving with a mass of 4m plus m. And we are interested in determining the speed that they're moving in. So this can be directly done using conservation of momentum. And we can say it is given by a fractional mass. In the denominator it would be 4m plus m multiplied by the speed that we only have, which is v. In the numerator we have the quantity of motion, which is related to 4m, so that would be 4m over 5m, which is 4 over 5 multiplied by v, and that would be b. However, you can do it using conservation of momentum. P initial is equal to P final, but you need to state that apply conservation of linear momentum. We have 4m multiplied by v plus 0. That would be equal to the total mass 4m plus m multiplied by the speed v that we need to calculate. Then v is given by 4m multiplied by v divided by 5m, which is 4 over 5 multiplied by v. Now a student conducts an experiment in which a cart of mass m1 is moving on a level horizontal surface of negligible friction with a speed vi towards a second cart of mass m2 that is at rest. The carts collide, stick together and move with a speed vf. The carts then travel up a ramp, momentarily come to rest, and then roll back down the ramp. The student repeats the experiment for several different values of vi. So here what we have, initially this is at rest and we have initial momentum to the right. They will stick to each other and they will move as a one body of mass m1 plus m2 with a speed vf. The students plot vf as function of vi and draws a best fit line to represent the line data. Which of the following expressions can be determined using the slope of the best fit line? So vf in terms of vi can be expressed as a fractional mass. The total mass is m1 plus m2, and in the numerator we only have m1, which means that C would be the correct answer, because if we're plotting vf as function of vi, then that's the slope. Now exercise 5, in the diagram above, a block of mass capital M is initially at rest on a horizontal surface at the base of an inclined plane. The surface and the plane have negligible friction. The block is struck by a projectile of mass M traveling with the horizontal VI. The projectile becomes embedded in the block and they move together to the right with the speed Vf. Which of the following is the correct expression for a Vf? So this can be done easily by, if Vf is the final speed, it would be a fractional mass, which is the total mass, factored by Vi, which is the only speed contained before collision, due to the mass m, which makes C to be the correct answer. And this can be done from scratch. So, or by saying P initial is equal to P final, then the initial momentum that we only have is mvi plus 0, which is equal to the total mass m plus capital M, multiplied by Vf. Then Vf in this case would be given by mvi divided by the total mass m plus m, right? Then let's move now to exercise 6. So C is the correct answer. Exercise 6, which is the final exercise for today's video. As shown in the figure above, a child of mass 20 kilograms who's running at a speed of 4 meters per second jumps into a stationary sled of mass 5 kg on a frozen lake. The speed at which the child and the sled began to slide across the ice is most nearly. Here also we're assuming that the system is isolated. Gravity cancels with the normal push, there's no friction. So the total mass is given by 20 plus 5, factored by the only speed that we have, which is 4, due to the moving 20 kg mass. So that would be 20 times 4 divided by 25, and the correct answer would be 3.2. However, we can do it from scratch using the conservation of linear momentum. Initially, we only have the momentum, which is given by 20 multiplied by 4 plus 0 because the sled is at rest, which is equal to the total mass 20 plus 5 because they're moving as a one body, multiplied by the speed v that we wish to determine. Then v is given by 20 multiplied by 4 divided by 20 plus 5, and that would again give us 3.2. Then thank you for watching and see you soon in a new one.